Hi, I'm Mark Himmelstein. I'm the CTO for RISC-V International, and these are the disclosures. Only RISC-V members may attend. This is in order to protect our IP rights. We have an agreement when we become a member. It's important that anybody who goes ahead and joins a meeting includes their name of their affiliation, their company, or if they're an individual, say individual, or an institution, so everybody knows where everybody comes from. We have an antitrust policy. We abide by the regulations in the United States and other countries. There is a link at the bottom so you can check that out. We are a collaborative and welcoming community. There's a code of conduct. If there are any issues, please contact as specified in that code of conduct website page, or send mail to help@riscv.org. But we're intending to be more than just not violating code of conduct. We want people to feel welcome. We want to have them feel included, and have them feel like they can share their ideas and not feel threatened in any way, shape, or form. We do have meeting conventions. We start our meetings for 1 hour at 5 after. We tend to try to not a rat hole. If there is a topic, then we either handle it in email or schedule a time to do that. We worry about people's time zones and other things, so we try to make meeting times. Obviously, there's a lot of competition for 7 a.m. Pacific time, and we try to accommodate as much as we can. So welcome to the meeting, and hopefully, if there are any questions, we can get them answered. You can always send mail to help@riscv.org, and thank you very much.
So,
yeah, maybe I can say a couple words if that's okay.
Go ahead.
Yeah, so we will take a look at making this available for non-members, but right now it's still a RISC-V venue, and so we're working that out. If you aren't a member, we'll ask you to actually step out. If you are a member, we certainly would appreciate if you put your affiliation in your name. That's easy to do, just on the side of your thing. There's a rename, and if you take a look at mine or Raphael's, you'll see what it looks like. That way, we know where people come from. These are exciting new meetings. They're intended to give you access to the technical leaders. So in this case, Robert, and we thank Robert for being the guinea pig. These aren't working group meetings. So if there are issues that end up having to be handled by the task group, we'll take notes and take those offline. This is more of everybody figuring out how things work. We try to keep the presentation to a short time to leave you enough time to ask questions and to have discussions. So you guys are all the guinea pigs, and so we really appreciate your coming. And if you have ideas on how we can make this better, we're a continuous improvement organization. You can always send mail to help@riscv.org. And over to you, Raphael.
Thanks, Mark. So today's speaker is Robert Chyla, who is a senior software engineer at RISC-V. Oh, sorry, at Sci-Fi. And he has been involved in high-end debugging trace for over 20+ years. And he is the chair of the Nexus ENTrace task group within RISC-V International. So Robert, is all yours.
Thank you. So I need to share my screen, right? So it's correct. Can you see my screen?
Yep, you're good to go.
Hold on a second. Let me organize some pop-ups here. Okay, I can survive. I think this one. Hold on a second. Okay. Anyway, so well, thank you, Mark, for introduction, and really, yes, that's the first of series, and announcement was not done so long ago. So I decided to jump in because ENTrace is approaching ratification, so it's a good moment to sort of explain it to everybody. And I really think that's a very good idea to have such a bi-weekly sessions, which will make everybody aware what's going on. So I hope you see my screen. Is that correct? And you can hear me?
Yeah, that's correct.
Okay, so let me continue. So today, yes, I will cover a session trying to explain the ENTrace, which is approaching ratification. And so let me continue. So agenda. First, as Mark mentioned, it should be a live session, and we are all guinea pigs, so I don't know how this will work, but let's give it a try. So I think I don't see you in here. It's the first time I'm also running a webinar like that, so everybody is testing. So ask questions maybe in chat, so I can answer them later, or even try to interrupt. I don't know if you can, but I can do that. So also another point is that's the agenda I want to cover. I will just not read it. Just please take your time and browse through that. I will not be going through every details in all the slides, because idea is also this will be posted, so you can like take time in your own time after the session, and then get more details than I will be sort of presenting. So the slides are pretty loaded, but I will not try to cover everything while we're talking. I'll skip through some sections. So let me then go on. So the first is just would like to explain what is it ENTrace, and I said it will be a packed slide, and this one is actually very packed, but as a picture is worth 1,000 words, so I decided to put it, and I will maybe put a few hundred on top of this to explain this a little bit. So first of all, ENTrace is a complete end-to-end program from trace from RISC-V hards, cores, and systems. Complete by complete, it means it includes everything. If you implement it, then you have everything together. And on this slide, you see different components, including on the right side, debug and trace tools on the host machine. These are not part of the ENTrace ratification process, but they exist already. So let me then, the second thing is it is based on well-established and Nexus standard, which is silicon proven. And another point we wanted to achieve, and I think we achieved that, it's utilizing all existing trace probes and professional trace tools, connectors, and the same which I used on ARM-based SoCs. So it means it's a good path from whatever was used before. You have the same tools. There's really no need to, for example, develop new trace hardware or nothing like this, because if we will do that, then it will be a very hard path. So that's making it smooth. And the good sign is as well that the initial version was implemented is already implemented in many RISC-V designs, and Sci5, who sort of pioneer this path on the RISC-V, has it implemented for over 3 years. And it includes the support for mixed architecture systems, because people are migrating from different places into RISC-V, and we are trying to embrace that. So let me go to the logical diagram of the ENTrace-based system, and maybe let's start from the legend. We have that sort of color, it's a raw trace flow on the left, and you have hearts in the system. These hearts are sending raw trace, that's what we call like raw trace, into encoders on the right. Can you guys see my cursor when I'm moving it?
Yes, we can.
Okay, that's good. So we have hearts or cores. That's always a debate on the RISC-V, what is what, but it doesn't matter that much. We have hearts. Each heart has an encoder, which takes the raw trace and makes it encoded trace flow, compressed. And then this encoded trace goes into what we call trace funnels. It's an optional feature. If you have only one heart, you don't need it. But if you have many, you must route the trace data somehow together and combine them. And on the left side, we also have a timestamping unit, which can be shared. So for example, all the hearts or all the encoders may use the same time base, like sort of wall clock. Everybody's looking on the same time, and you have different events in the system. You will see them, timed properly. You can also timestamp by clocks, which each core can be a different, different clock cycles, for example. Another point in here is important component. RISC-V systems have a debug access, which is ratified, and all the access to the trace controls. That's why the green elements on the screen, this one, and this one, they are related to a debug. And green arrows shows the flow. I couldn't flow the control properly, but you need to understand in here that the trace components controls, which controls all the components, are accessible through the system bus and debug DM. So that's important feature. I will talk about it a little bit later. And we have also some external components from the trace perspective. Ingress port is external from a trace. It is already ratified as a part of the ENTrace specification. So that's in here. On the right side, we have trace connectors, which are actually defined by ENTrace specification. And we have, for example, some other interfaces, which are a bit external. So let me continue with the trace flow. So you have the routing network, which the trace is routed inside of SOC, and then it may go to one or many, even if you want to, different destinations which are called sinks. So trace is coming from a heart and goes into the sinks somewhere. So the system defines 4 different types of sinks as in this moment. So we have SRAM sink. It's a small RAM inside of SOC where you can store your trace and restore it later. And for this one, it is part of the trace control. You can take the data out of SRAM. See, this SRAM is inside of the sink. It means it's not accessible anywhere else. Just it's a local. So it's not memory mapped device, but trace control itself is. So you can somehow take it. The other, maybe let me go from start to the bottom. So the other component, which is similar, is what we call SMEM sinks, the system memory. Here the acronyms are described. System memory sink. It means the trace may be shoot to system memory, and that's the blue storage where it may be stored. Of course, you can't utilize entire system memory, just part of it, but that's possible. So if you have a big system, you may, if you want, you may dedicate some like gigabyte or something to a trace. Another option is the PIP sync. PIP means pin interface block, or sometimes it could be called probe interface block. Is sending data, trace data out of the chip through external pins. As of today, I will talk about it later. It is serial and parallel options, and we have the connectors on the pins defined, and then it goes to external trace probe. Yet another option, we don't call it sync because it's not the final destination of a trace, is a ATB bridge. ATB is acronym for Advanced Trace Bus. It's ARM defined it. So you have mixed ISAT system. You can export RISC-V subsystem trace and combine it in ARM based infrastructure. So going right, and all this in this box is defined by ENTrace specification. All the controls for timers, for funnels, for all the sinks. So that's part of the spec. Going right. So once you produce the trace, you can either read it from RAM, either small RAM, or just you can see it on the system memory, take it through a debug access, or you can shoot it out to external trace probe, and this probe then can do 2 things with this. Trace probe may store it to a file, or some trace probe may give you access to the trace memory. So the storage is either in the trace probe or it is being streamed to a trace file. And of course, once it's being stored inside, you can also store it to a file and analyze it later usually. So here, this is just a sketch. As I said, spec does not define that part, but that's usually what people do. And I was doing this right side for many years myself. So usually trace systems, that you have the trace control, which you have GUI, you enable things, it could be command line or some scripts. and then it is always combined with the access to the debug subsystem, and then there's a separated trace viewer. Analyzers also could be Windows or command line or some sort of scripting. And the important component is kind of small here, but that's, I think, the very important component is trace decoder. When you take the trace, you can decode it and then present in a human readable way. And as you see here, the trace decoder may take it either from a trace files or can take it usually from inside of a trace probe. That's also important thing in here, the L files. A trace decoder must know the code which is running. So trace is so compressed that you cannot tell what data is there without looking at the code. You basically need to consult the binary code, not source code, but binary code. So could be bin file or hex file, but we sort of usually call it L file. So to be sure how your program flow goes. You will understand that a bit later. So let me then continue with that. We can return to any of these slides. I would try to sort of go fast, but we can return to the slides at the later if needed. So let me move on. So this is about the trace encoding principles, which I hope are simple. So let me read this really quickly because I really want to have a bit more time for answers. So in general, Court is sending blocks of retarded instructions at the recycle. So on that left side, Core is spitting the PC flow, and then anything which is linear, like normal additions or something, or anything what you can find what's an address from looking at the ELF file generates no trace. So basically, if the code is like 20 instructions in a row, there's no trace out of it. So only indirect flow changes, like for example, calls of functions, exceptions, returns, they usually generate an address drop. And this is compressed, so we don't send 64-bit address every single time. It's using extra mode, which if the addresses are short, close, the address is short. If they are far, they are bigger. Also, periodically, we need to send a full address, otherwise the decoder will need to decode everything from the beginning to an end. So periodically, it's assured that there's a periodic address, and decoder can trace from the middle. You don't have to trace from every beginning. So if you are tracing for 10 hours, you hit a sort of crash, you can go backwards like a little bit, like half a megabyte, and then you can decode the trace, something like that. So also the exceptions and privilege levels needs to be traced, so there's a full awareness how the program goes. Also, on every conditional branch, which is in RISC-V is always PC relative, you need to trace. Otherwise, because this you don't know if the branch was taken or not taken, so you need to do something. And ENTrace lets you do 1 bit is added to a special history buffer, and this buffer is being set outside. Some extra features related to encoding, there are triggers, so you can start and stop trace, and it of course produce some packets, but these are not like a main flow data. Main flow data only includes this what I say above. Also, as was seen on the graph, several encoders may send trace at once together and will be combined and sent to outside. So that's another. And also timestamping is possible, so you can timestamp messages or not. Nexus actually provides a very nice feature that it's up. Any message may include a timestamp, but also some messages may not include it. So it's a very good balance, because not always you want to include the timestamp. And this is all sent by very nicely clean formatted stream of bytes, which is 100% Nexus compatible. And just these bytes include 6 bits of data and 2 bits of framing. So it is very nicely encoded. So let me move on. A bit of history of Nexus and ENTrace. So Nexus, as you see, was mature, released in 1999, and version 2 was released in 2003, and version 3 which added Aurora high-speed trace option, was released in 2012. So more or less, we are compatible on version 2 because that was the addition. We don't right now. ENTrace does not support Aurora protocol, doesn't sort of blessed it from Nexus. So it is almost 20 years ago, but it's a very potent format. That's why it's big, and it's implemented on non-RISC-V cores many times. Here's some, details: PowerPC, ARC, IVR, even early ARM cores had it. ARM, however, didn't fully embrace Nexus. That they go with CoreSight, so that's kind of made it slightly forgotten feature over the last 20 years, but it's there. And Nexus debug was also never sort of mainstream because everybody goes through the sort of plain JTAG debug, including RISC-V, but trace is very simple and elegant feature. So December 2019, this TG was proposed. It's a quite a time, but we wanted to do a good standard, not rush it. In March 2020, Sci-Fi implemented it and released as a form of inside trace. And then I was in IR and I put the reference decoder in that time frame as a part of TG. And after that, Sci-Fi donated the trace control interface to Nexus TGs. So then the real work sort of started. And so right now we are approaching the ratification in Q1, 2023, which is sort of today. So let me move. This is just an ENTrace ratification plan. Most parts of the ENTrace specifications are on internal freeze. They have different PDFs, and main work right now just on a last stretch of a runway. We are trying to make sure everything is nicely described. There's no ambiguities. Nexus itself is very flexible format. So if you say, please implement Nexus, there will be a lot of problems. So we are trying to make sure the things which can be, solidified are solidified. This what should be flexible stays flexible. Also, we have an ambition that ENTrace specification will be standalone. It means you don't have to read anything else to implement it, and either in silicon or a tool. Also, the reference written in C encode and decoder should be used to assure conformance and help with development. Official freeze will approach in February 2020. After this, there will be 45 days of public review. And after public review, there will be some votes on the different levels in the RISC-V International. And so expected ratification is Q2 2023, May, June, something like that. It depends, the ratification can't be done from day to day. So that's how it goes. So let me move on. So what is handled by ENTrace TG? So there are some pages. There's a main page. You will have these links. There's a GitHub repository. Reference code is there. PDFs are part of the repository, has a different placement. That's the charter from it. Again, it's complete end-to-end program, and this has several components. Trace messaging protocol, which is 100% Nexus compliant, plus extra options for better compression, trace controls and configuration, on-chip trace and off-chip trace, serial parallel. It also defines 2 trace connectors, non-expensive MIPI 20, and these connectors are following the MIPI and ARM standards, and also industry practices for over last 20 years. So, excuse me, there are two connectors. One is non-expensive 4-bit, the other is high performance. They have different clock rates. It's up to you. And then this all is already supported by numerous trace tools vendors, and these connectors are extension of RISC-V debug connectors. So somebody has a debug connector and they want to put the trace connector. Debug will of course work on this connector, and also if you have a trace tool and your board doesn't have a trace, probe vendors provide different sort of adapters, so that this is not a problem over there. So let me move on.
Robert, we have one question.
Yes.
You want to take that? So Jan, go ahead. You are on mute, so you can unmute yourself and ask the question. He wants the link. Okay, go ahead, Robert.
Okay, so yeah, I think please put questions to chat so we can go through them, after,
Yeah.
I'm
I think it's a Q&A actually instead of chat.
I see.
So if they go to Q&A, they can go ahead and add a thing.
I see. Okay, so let me move on, and we'll go there. But yes, if an interruption is possible, just go ahead and do it. Anyway, so ENTrace, as any sort of other trace, can be used for what I call traditional debug. That's, people think that's the most useful form of tracing. There's, like I mentioned, a $1 million bug, right? That you can find a bug which makes your product running. I often joke the $1 million bug means that you already spent 1 million trying to traditional methods, and then you come to the conclusion, oh yeah, I need a trace, and you buy a trace prop, and then you have the $1 million problem solved. Anyway, so that's a traditional debug. And even if you don't want to provide a big infrastructure, small dedicated RAM, 4 kilobytes, which is 32K bits, will provide a lot of trace. And it is really not expensive to activate. Traces, just to activate, it's just one write or two. And I sort of, that's what I call it, always on trace, means you should wear it. We don't wait to buckle up in a seat belts after a crash, right? So we do it before. So that's my sort of idea for the trace. It's also important for code coverage, and which is basically a must for safety critical applications. And because every branch now is taken or taken, it's known, and everything flow in the program is known. You know how many times a particular if was executed to the left, to the right, so that everything is visible. This is also what I put it here specifically because coverage can be also used in what I call traditional debug. If many of you, maybe you are guys programmers, and as I am, many times you say, oh, I step way too far, right? I step over the function instead of sending inside. Trace will give you that information. And by looking at the coverage, okay, this if was executed, this was not executed. That's a great feature. Also, another thing is performance analysis, where the events in trace can be timestamped. So you can see that. This is maybe too early because I didn't explain the modes yet, but there's two modes. One is better compression, other is less compression. That's one of the advantages of the sort of not so good mode, is that it has a better timestamp accuracy. So you see better because you have more often traces coming out of the chip, so you have the timing information in the better quality. And also in the multi-ISA configurations, what we call the other leading architecture, so you can combine the trace with that using ATB bridge. It is suitable for small cores and large multi-core systems. Very basic implementation can be maybe small. I'm not on that side of the things, but that's sort of obvious once you see it. C implementation is almost one page of a code, so VHDL can be like that as well. And also supports serial UART and Manchester to low pin counts devices, which is important on some areas. Also, it provides live streaming capabilities, so you can do this. Depending on here, I'm talking about the bandwidth of the different probes. They are about 1.2 to 12 gigabits per second, depending on the connector. Because for example, Mictor can go 400 megahertz, MIPI20 can do 150 or even 200 if you're lucky, but I don't want to stretch too much. Also, the in-system trace is supported. So, for example, Linux kernel may be tracing single application or more than one. It is also fully supported by ENTrace. So let me move on. Here, I'm trying to talk about trace compression techniques. So basically, basic ENTrace is 100% Nexus compatible. Nexus has two main modes, which one is called basic branch trace messaging and history trace messaging. I will explain this a little bit later, what are the differences. BTM has less compression, and there's no the need for message at every taken branch. So every branch you have a message. So if you have a timestamp with it, you know the time of every taken branch, basically. So it is often. HTML, though, provides more compression, and we have only single bit per taken, non-taken branch. It means you can't see all the timing at all the branches, but the trace is much more compressed. We also utilized and added, this is the sort of permutable extensions to a Nexus standard. First extension, they are put in the order of sort of importance and how I see them. First is a repeated history. If you have a long loop, then usually it will, like you have, for example, memcopy 4 megabytes, you have, and even using 32-bit transfers, it will execute 1 million of branches because it's a loop with if, right? While or if or for or something. So you have 1 million branches. It means you will need to 1 million of bits, right? Even if you have 1 bit per branch. So instead of sending 1 million of bits over the trace, you can detect it is repeated thing, and then you can just send one message with a pattern of branches and a counter. It's important. It's not only a single, say, always branching or not always branching. It's a pattern. So if you have insight of the loop, this will also work very nicely. You will see that later. The other important compression is what we called return address stack, and it's also called implicit returns. So as you noticed before, every unknown address needs to be sent. Could be very short, but still needs to be sent. And return, by definition, you don't know, by looking at the code of the return, you don't know from where will be returning. It's returning usually to a call place, right? So after a call, it returns to a next instruction after it. It means that if encoder will track the call, so every time the call is encountered, you push an address, return address on a stack. If encoder will say, okay, it was a call, now it's some code which doesn't call anything. Let's assume it's a leave call, so it doesn't call anything else. It just loops or runs simple, and then you see a return. Then instead of emitting an address, you just do nothing, and you pop up the address from a stack. If address is different, you just report an address, but if address is the same, you don't have to do anything because the decoder is seeing an address, or call address, call destination, call everything about this instruction. So decoder may find out where the code is returning, if it's proper return. If it's improper return, because for example, you have a RTOS or you have a damaged stack, then it will be still reported, and you know where your code went into the weeds instead of going into proper place. So with that option, you will see it on the next slide. It is enormous compression, and you will see it because and also it's multi-level. So you have calls and calls and calls. So basically, if you have a program which doesn't do anything fancy, it just calls functions and have loops, all you have in trace, because you almost have no addresses. You don't need addresses because all the calls are into fixed addresses, and the returns are to this sort of fixed addresses as well. So only thing which you are tracing branches. If branches was taken left or right, taken, no taken, taken, no taken. And with the compression history, this one, repeated history, you may have very small trace. And I will show you that. The another thing that's a sort of because of a RISC-V architecture feature, I'm not sure if everybody knows it, but perhaps RISC-V cannot make far direct jumps and branches because of the encoding of an offset. It's always an offset from a current PC, which is small. I don't remember exactly what it is, but it's I think 12 bits or maybe 16 bits or maybe even more, but it doesn't matter. It's limited. So in order to normal code to make far jumps or far branches, it needs to be done by 2 instructions. First is setting MSB part of that address in register, and second is a jump relative to this register.
Hey, Robert.
So, yes.
I just want to do a time check. There's really only 20 minutes left, so we really.
Okay, I have one more like one more slide, basically, which is I think sort of important. That's I'm looking. Thank you. So these 2 instructions can be detected, and then it makes no trace. Okay, so that's the sort of the key thing, in my opinion, trace compression results and analysis. In here, I am trying to show BTM mode, this is basic mode, and then 3 different HTML flavors. This is without no repeat. This is with repeated instruction, and that's with repeated instruction and return stack, 8-level deep. So let me look on this one. On each of these, I report the gain. What's the gain of this one comparing to previous one? So HTM gives you, some gain. I will go through that later. So we look only on the embedded programs. These are some, because they are more real. There are core marks and dry stones here as well. And these programs are kind of small and it's sort of strange, like Towers of Hanoi. Some very, very, see they're smaller. These one are bigger. There's a number of instructions. We also, the CRC32 is excluded because it just includes crazy looping. This out of the blue kind of. Basic HTM gives you 2.3 times better than HTM. It's 200% on average. Some of these are 700, 800. So HTM provides a lot of good, things. The lowest is on this one actually, but 60% at least, and on average 2.3 times. Repeated history, that's comparing this one to this one. It's usually nothing, because not all the programs have repeated patterns or a lot of jumps, but this guy, it skyrocketed 26 times, right? Why it's so? Because this is CRC32 algorithm. It has a lot of looping with a lot of same, code. So that's why it was so heavily compressed. So, and return address stack, it provides almost 80% on average, some 500. And see, this one was very poor. On the red side, kind of the bits per instruction. That's the compression we calculate. So it was very poor so far, but it got improved by return type, because dry stone is actually nothing but calls. So if you enable the call compression, then you gain a lot. So you see here, this is 591, and this one, if you look, what is it? It's a Towers of Hanoi, which everybody knows it, right? From even early computer classes. That's a recursive algorithm which has nothing but calls, no code, just calling like crazy. Here as well. So total gain, if you compare this number, the number of bits per instruction with the last one, 0.2, it's 6.5 times, which is a lot. So it's worth to implement full implementation. Compression is of course code dependent. You see different programs compress differently. I don't want to go too deep. It's a compiler option dependence as well. But some programs, the gain is huge. And average in this one, 0.2 bits per instruction is just excellent in my opinion. So if you have 1 gigahertz core with 1 instruction per cycles, it will generate 200 Mbps of trace. If you want to scale it to your chip, you can do it. This will provide very good external trace. It's really no limit on the bandwidth if you go to internal RAM, but if you go outside, there is. So with that number, it will be very good. And also PIP, it provides the calibration option. And these are the basic data which already was talking about. And you can use reference decoder and encoder to get this data. So I think one more slide on a summary. So please wait for official freeze and read the spec. Right now, we were approaching and cleaning stuff a lot. So don't read it now. For example, some things are not in a public place in this moment, but we are, clarifying things. You can use reference C encoder decoder to test your divine. You can join Nexus TG still, and then you will be, aware what's coming on the last days, and you should participate in 45 days review if you are interested. Some future directions. It would be good to provide the VHDL reference encoder. There's a C model. It's simple. I hope somebody from RISC-V community could help. Feel free to reach out. ENTrace will be extended to add, for example, data trace. Nexus defines this all, but we want it to be program trace only, and that's what it is, plus entire infrastructure. So that's why adding data trace is small thing. And also this ambition, maybe the RISC-V ENTrace transport infrastructure could be reused for performance and system level trace. And Nexus also defines messages for that. So that's about it. And I'm open for question and answer. Should I just open that Q&A channel? Because I never did that.
Yeah, there's 3 questions there. I believe one you have answered. The first one came from Stefan on what is the approximate compression ratio for the encoder that you have talked about a lot. There's one question from Michael about
can you guys see the chat on my screen? Or no?
Think you can. I think you can.
Yeah.
You can open the Q&A.
Yeah, I opened it, but question is everybody able to see it or no?
Oh, they can. If they open, they can. They just need to click.
I see. Okay. Okay. Yes, so compression ratio, let me read it because I can see it, so I can sort of go through this. Yes, compression ratio, you've seen it's published, so you can, but it depends on some factors. The second question is empty from ENTrace. Right. Examples. Yes, we are working on the infrastructure. Second questions, because I don't want to put. In order to do that, we need to have an L files and also the PC flow. And there's many files. So I am right now, as we speak, I'm working on to provide a single file, and the testing scripts will extract the data from it. Because I don't want to put like whatever 20, 30 ELF files and big files in the GitHub. So this will be worked on. Yes, it's still on the clearing stages. Data trace and instrumentation trace, Tomasz Zinder. Yes. Right. So this will be addressed.
So Robert,
yes.
why don't you repeat the question so that everybody knows?
Yes, of course. Yes. So what about data trace and or instrumentation trace? There seems to be only ownership trace is typically used to signal process switches. Well, not only there's data messages, and this will be addressed. And actually, it's not a secret, but Sci5 has it implemented. But ENTrace itself doesn't have that capability yet. But it was in here on the that's why it goes selective, and instrumentation trace will be the first to address, because it's desired to match Cortex-M ITM and this kind of stuff. So you can use it for different things. Right. Another question is, what is the relation between ENTrace and ENTrace? Do they compete with each other or have their own purposes? Or question mark. Yes, I didn't address ENTrace a lot. ENTrace is basically, let me then go to that. It's an encoder. It's a different encoder. The ENTrace does not embrace entire infrastructure. And actually, when we in ENTrace ratified control layer, it is ambition to, and is a fact actually, to reuse the same control layer for ENTrace. So people will have an option to either choose ENTrace encoder or ENTrace encoder if they want to. And ENTrace right now, it, for example, provides a data trace option, ENTrace doesn't. So these are the differences, but end of the game, the compression ratio are similar. So you know, this is the same programs. I didn't publish this data, but it is available on a TG. I publish it on some meetings. So the compression ratio are similar, but the ambition is ETrace is just an encoder. It's a piece of the, if I go into, maybe let me, I don't know how to slide it. Oops, sorry about it. Let me go in here. So that's where it's an ENTrace encoder, or could be possible ETrace encoder in here. So that's where was the relation between these two. ENTrace did not define all of this. Oh, there's more questions. Okay, hold on. So can you elaborate whether Nexus is a live standard in active contemporary high volume use to other major architecture? Is core site item proprietary? Are they other trace standards widespread used right now? No, there's no other standards, widely used. MIPI provides some standard, but these are also closed standards. You need to, and they are more or less ARM based or similar to ARM. But Nexus is, we can embrace it. It's actually Nexus is no longer existing. It was shut down in September, I think, last year, or even almost 2 years ago. So and actually some Nexus guys from Nexus were part of a Nexus Trace TG in here. So we kind of inherited a Nexus into RISC-V, and that's we call it ENTrace, because the reason why it's called ENTrace, because it is not everything is Nexus compliant. Trace controls are not, because the Nexus trace controls were kind of mimicky and connected to a Nexus debug, and people don't want to do Nexus debug. They want to do RISC-V debug. So that's why this was done like that. We only took the Nexus messages, not a debug infrastructure. But other question, does ENTrace improve the performance or utilization of SoC? Of course, because it will improve software, but it's not changing anything. By definition, any trace tool must be 100% non-intrusive. So by itself, if you add it, the core will not run faster, but if you add it, people can run better code. So then the code, the SoC will run faster. Any ideas to handle the dynamic self-modifying code? That's up to decoder to know, and usually when you have the dynamic code, the self-modifying code is crazy. If you do that, you just want to kill yourself. That's my opinion. But if you have generated codes like translations, the stuff like this, if the encoder is aware what was the code which was running, it can decode that, because every sort of branch outside of the normal ELF is detected, and so you can do that. It's not being specific addressed, but it can be handled with a bit of sweating. For your information, MIPI debug spec are publicly available and not ARM based. That's true. MIPI debug specifications are available, but I don't want to go into MIPI debug. It's about the trace. So it is not about debugging, because there's no ambition to change the RISC-V debug in this moment. And actually, when I heard when RISC-V debug started, they were looking at the MIPI debug, but it was closed in that moment. So MIPI has part of the specs are open, part of them are members only. And I think RISC-V ambition is to be 100% open. So that's why this is open, and there some work with MIPI, like for example, connectors. We sort of ask MIPI to add a trace feature to MIPI 20 connector. It wasn't added there. And MIPI actually published that from a push from this TG, but the MIPI debug, entire MIPI debug, is not embraced, and it's not part of the thing. MIPI is talking about the I3C debug. There's some other debug methods, but that's outside of the scope of the ENTrace. Okay, it's growing. More questions. Can multiple things be used simultaneously? Yes, it is possible. You can do that. Each of the things can be individually enabled, so you can shoot the data to more than one. And one of the use cases, it's aggressive in the spec, is when you have a very small RAM close to each core. So instead, on this picture, right, you have the SRAM sync, and in the big system, usually you have the small RAM close to the core. Each encoder may have its own small trace, but there's a big trace everywhere. So for example, if you have a big system, you can trace few cores outside, but all of them inside. In the case of crash, you have a lot of history, but you are not overloading the the system level trace with all the trace from all the cores, right?
We
Good
have
question.
a question from Iran, so he raised the hand. So any questions you'd like to ask verbally?
Yes, there's another question. Okay, if somebody wants to speak out, please speak up. But I have another question in the chat. What's the debate on heart and core? I remember you mentioned something about it. Well, it is, some people implement heart as a core. Some debuggers, it's also in the debuggers like GDB, they don't know nothing about the hearts. There's a course. Usually there's a term multi-core debugging, which is actually means multi-heart debugging. So heart in general is a subset of a core. It is, core may include more than one heart, but may sometimes include just one heart. So it was it's a same as about endianness debate. If you start it, you never finish. So, but heart is a RISC-V term, but core is more, more known. But same with the hyperthreading, right? On an Intel cores, something like that. So here one more. The trace low-end MCUs. Right. So question to low end like MTB. I believe the small implementation will be the same as the MTB quality. Still compressed. MTB is uncompressed trace, but I think implementation for very small core is possible and small enough. You can, of course, you can't beat MTB because it just stores addresses, just more or less raw port encoded. But right now we don't offer uncompressed trace. But BTM mode, the primitive one, it just provides very, very small implementation. I can address that later. Is the system defined by ENTrace? Yes, it is. The sync system bus is defined, but everything in that box is defined by ENTrace specification. Yes, the another question, with multiple hearts, is there a way to time correlate traces from each heart? Yes, because the timestamp unit is shared, so you can timestamp traces differently. Also, the messages will be in a proximity, that they will be joined together, but funnels shouldn't hog. They should merge the trace, switching between sources often if both of them or n of them provide the data. So the protocol is completely costless. You can do it without any extra overhead. It doesn't matter how often you switch the data. So you may have piece of trace of this core, piece of trace of this core, and they will be coming one after another. It means they're in a close proximity, even if you don't enable timestamp. But with the shared timestamp, you will exactly know the time. Dynamic or dynamics, self-loaded images or self-modifying code can be traced if you have data trace capability to signal when on which address code was loaded. Yes, that's true. Dynamic, like even Linux level loading of dynamic images is a challenge. For this, we do have like process ID so the trace tool can consult a kernel where the code is. And basically, if you know Linux enough, all the applications are running on the address 0, kind of in the same address space. MMU setting is different, but this can be handled by a Linux kernel which sends the process ID. So debug tool and trace tool can take that into account. It is being done, you know, over many years, and it is actually working on the RISC-V as of today. And I think no more questions. I reached the end of the Q&A, so I'm answering faster than people are asking. Oh no.
I think we are good. So we have, I'd say, 40 seconds. So if you
yes. So one last question is a good question. Is there any open source hardware supporting ETrace or ENTrace? ETrace has CPU, ENTrace, trace encoder. They're both the same. They're both trace encoder. I don't know. I know about ENTrace. I am not aware about any open source implementation. ETrace, I think, may have something preliminary, but I can't answer that question. Please shoot it to I will try to answer this on the Nexus TG if I think somebody will save that list. I hope.
Yep, I'm going to save all the questions and send to you.
I can answer the questions in writing, sort of, so you have it as a record as well. Any more, or we are done? It's 8 a.m. Oh wow!
Yeah,
I think we are
done. Yeah. So I'd like to thank you, Corbett, to be the first one to present here, and thank you everyone that joined it and stayed with us until the end. The recording will be available, and then I'm going to notify everyone when we publish it. So the next session.
Right, and also I'll provide the PDF of this presentation as well. Mm-hmm.
And also I'm going to send an invitation for the next session as soon as we get it organized. So,
thank you everyone, and it was really a pleasure sort of being a guinea pig, but that's nice.
Thank you everyone. Bye-bye.